Hello, this is Tak here, recording this from home or streaming from home. So I'm going to get started with the practice tests. Particularly, we're going to go over proof by induction as well as proof by contradiction today because those topics will be in the test. All right, so both of those topics were introduced before. It's just that we introduced and apply those two proof techniques kind of on the way to prove something else. Proof by contradiction was introduced when we talked about propositional logic, and particularly when we talked about how to use proof by contradiction in conjunction with resolution in propositional logic. Um, the other one is proof by induction. Proof by induction was introduced when we talked about the binomial theorem, and I believe that is in discrete probability. So these two are the topics where those two proof techniques were first introduced. So I'm gonna just go to these individual slides just so that I can point out where you can find the source information, and we'll add some more stuff later in this lecture. All right, so this is propositional logic, and in propositional logic, proof by contradiction was introduced in section 5.4. So section 5.4 is when we introduce proof by contradiction. And the idea is we have psi being all the facts that are given. So these are not to be challenged or negated. Phi, on the other hand, is a theorem. In other words, we want to find out whether all the given facts would imply the theorem. Because in order for something to be a theorem, it has to be implied for what is known to be true. So we want to know whether this is true or not. That is the objective. But based on the corollary that we talked about a little bit earlier, which is this part here, with any type of implication, you can add a component using a conjunction. And as long as you add that conjunction component to both sides of the implication, if the original implication is true, then the modified implication would also be true. So in this case, if phi in fact is a theorem and psi implies phi, then we can introduce not phi, which is the negation of the theorem, on both sides of the implication without changing the truthfulness of the implication itself, which also means because on one side we have phi and not phi, which automatically becomes false. So we know that all the given facts with a conjunction of the negation of the theorem has to be implying false. And that is the whole basis of proof by contradiction, is you combine the negation of the theorem that you're trying to prove with things that are given to you as as confirmed true, and you should arrive to a contradiction. On the other hand, when we talked about the binomial theorem, we talked about proof by induction. So when we go to the binomial theorem, this one is proof by induction. In proof by induction, there are two steps. The first step is the base case. The base case is when you have to basically select a case, select one instance where the theorem is trivial to be proven to be true. So in many cases, we choose n equals to 0 or x equals to 0. Basically, we choose a point where it is easy to prove that the theorem is obviously true. And then what we do is we have at least one induction step. Sometimes we have two, but we have or more. But an induction step is basically making an assumption that the theorem is true for the case when n equals to k, such as in this case. In this case, we assume the theorem is true for the case when n equals to k. So we have to use this particular assumption to prove the very specific case that when n equals to k plus 1, that the theorem is true as well. So the assumption, between the assumption and the case that we are trying to prove, it has to be only off by one or one step whatever that step is. In most cases, one step is just exactly one as a value, but sometimes one step can be two, can be some other numbers. But in most cases, especially in this class, one step is just one. So those are the two techniques that we'll be going over today. And so what we'll do is we're going to open up the past exams again. And then we'll take a look at those particular proof cases. So we'll use the exam from last semester first. And in this case, that's question number 1. This is question number 2. So in this case, question number 2 is the case where we have to prove by induction. So in this case, as with any type of proof by induction, you have to state, okay, I haven't signed in yet. Let me sign in first. So that this way I can change the document. Okay. Okay, now that I signed in, I think I can just go there and refresh. That should register me as signed in. Yep. Okay, so I just signed in, and here we have. Okay, so question number 2 is the one that we're trying to deal with right now. All right, so my answer to this one, I just got some email. I'm guessing some of you sent me email because you were noticing that we are streaming. Yep, I do not see any email, but I see many icons on the screen, which is cool. Okay. All right, so in this case, we choose the base case to be the one when x equals to 0. Okay, in the base case, we say, okay, let's consider the theorem when x equals to 0. And according to the definition of f, this is the definition of f, is when x equals to 0, then by definition, f of x is 0. So, but the theorem is trying to say that f of x is actually x itself. So let's see how this works out. Okay. When x equals to 0, f of x equals to 0 by definition. But when x equals to 0, x is 0. Okay, I know this sounds like lawyer talk, but that's basically the way it is. And as a result, f of x equals x when x equals to 0, and the base case is now proven. The induction step, there are 2 induction steps in this case because we have to go forward, when x becomes larger and larger, and also we have to go backwards when x becomes smaller and smaller. So we have to say induction step 1. Okay. Assume the theorem is true when x equals to some value k. Okay. In other words, f of k equals k. Okay. We want to prove that the theorem is also true when x equals to k plus 1. So this is the objective, because we want to prove that the theorem is true when x equals k plus 1. So the way we prove this is this. So we need to, Google Documents doesn't really let me use LaTeX in the way that I really want to use it. So this is going to be a little bit harder to read because I can't really use the notation that I normally use, but it's okay. So we'll say f of k plus 1 equals 2, and this is going by the definition here. So f of k plus 1 is f of k plus 1, the whole thing, let's see. Oh, f of k plus 1 minus 1, and that matches this portion, and then the whole thing plus 1. Okay, this is just by definition. And then we can now say So this really boils down to f of k plus 1. And the reason why it boils down to f of k is because we got k plus 1 minus 1 here. The plus 1 and the minus 1 cancels, they cancel out. And as a result, we only got f of k left. And this is just k plus 1. So this is the end of that particular proof. And I'm going to add some comments here, okay, by recursive definition of f. Oops, I have a typo here. There we go. And this one is by induction assumption. Oh, no, this is canceling. So plus 1 minus 1 cancel out. And then the last one, this is the one where we use the induction assumption by induction assumption. So that's it. That's induction step 1. And we're going to go with induction step 2. So induction step 2 is about the same. We say assume the theorem is true when x equals k. So the first part is the same. Okay. And we can also repeat this part here. Now, obviously, in the test, you don't have to be as verbose because I'm typing it. I can do it relatively quickly. But this time, we have to prove that the theorem is also true when x equals to k minus 1, because we want to be able to go negative. So in this case, we say f of k minus 1 equals to f of k plus k minus 1, the whole thing plus 1 minus 1. And this one is by definition. It is by this particular definition here. Let me just kind of highlight which one we're talking about. It is by this particular recursive definition. By recursive definition of f. And then we basically use the same technique as last time. So this boils down to f of k minus 1, because minus 1 plus 1 cancel out. And by the assumption, the induction assumption, this is just k minus 1 by induction assumption. So now that we have both the base case and the induction step to go positive and the induction step to go negative, we're done with this proof. And that's this particular one. Okay. And then we're going to move on to question number, let's see, number 3 is not any proof. And question number 4 is proof by contradiction. So let's see how we can deal with this one. So we can now say that, so I'm going to use, just spell outside here, because otherwise if I insert equation, it's going to take a little bit longer. So psi is the given fact, which is, tag randomly drew 7 socks without getting a single pair. Okay. Phi, on the other hand, is a theorem. The theorem is saying that tag has at least 7 kinds of socks. All right. So to prove this by contradiction, we have to say, okay, what is the negation of phi, which is the theorem that we're trying to prove? So let me just emphasize here. Theorem to be proven is phi, and no fact is psi. There we go. Okay. So not phi in this case is basically saying tag has at most 6 kinds of socks. Okay. So what we want to do is to say we will combine psi and not phi. So when we combine these two, it is basically saying tag randomly drew 7 socks without getting a single pair. Okay, some typo here. And, okay, so there's an and here. And tag has at most 6 kinds of socks. But this part here, okay, implies that I have 7 kinds of socks. Okay, so tag has in hand 7 kinds of socks, and tag has at most 6 kinds of socks, and that has to be false because this statement that I'm holding 7 kinds of socks in my hand because I drew 7 socks out of the drawer without hitting a single pair. And the negation of the theorem, which is saying that I have at most 6 kinds of socks, they cannot be both true. And as a result, we have a contradiction. So what I'm looking for in terms of grading is that people know how to structure a proof by contradiction. By that, I mean people have to identify what is the given known fact and what is the theorem to be proven. Okay, so that's the first step. The second step is to negate the theorem that we are trying to prove and state that negated theorem correctly. And then the last step, which is the tedious step, is the actual proof. The actual proof will combine the facts that are known to be true and the negation of the theorem, and then that's and there has to be some kind of argument. It doesn't have to be fully mathematical or symbolic proof, but it has to be some kind of argument to show that the conjunction of the known facts and the negation of the theorem will lead to false. That is what I'm looking for. It's just more of the structure of the proof, because just showing the structure of the proof is worth quite a bit of points already. But finishing the proof obviously would get all the points. So that is the discussion of these 2 techniques from the Spring 17 test. So I'm gonna take it away for now because this way I remember which one I have already talked about. And this is Spring 16. We'll take a look at the Spring 16 test. So in the Spring 16 test, we got this question here. So in terms of structure, it is kind of the same as the other one. So we'll go ahead. I'm going to go ahead and remove all these rules here or lines, just to kind of guide to help you, write your proof without kind of writing in a slanted way. Okay, so in this case, same as the last one, we have to identify our base case. So the base case is out of the entire range of values where the theorem is true, you basically just pick the one that is the easiest to prove. So in this case, the base case is when x equals to 0. Okay, so when x equals to 0, f of x equals to 0 is by definition. But at the same time, the theorem is trying to prove that f of x is just x squared. So in this case, we can say, when x equals to 0, x squared, I'm just spelling it out because I'm too lazy to use equations here. So x squared is 0. As a result, when x equals to 0, f of x indeed is x squared. Okay, because f of x equals to 0 is by definition, but then x being 0, 0 squared is also 0, and that's how we prove the base case. The induction step in this case only has to go in one direction, so in some way this is easier than the previous one, but there's a little bit more algebra involved, so it's both easier and harder at the same time. So in this case, the induction has to say, okay, the assumption of the induction, assumption of the induction step is the theorem is true when x equals to k. In other words, f of k is in fact k squared. Okay, so now we have to say prove that using the induction assumption, prove that f of k plus 1 is k plus 1 the whole thing squared. That's what we're trying to do. So in this case, I'm going to use equation because it's just a whole lot easier to do it this way. So I'm going to insert equation here. All right. So now we just say, okay, f of k plus 1 by definition is f of k plus 1, oops, k plus 1, the whole thing, minus 1 plus 2 of x. So in this case, it's 2 times k plus 1, and then the whole thing minus 1. But using so this becomes the f of k plus 2k plus 1. I just combined the steps here because this is the 2k comes from here, and then the plus 1 is because of the 2 times 1 minus the 1 on the outside. So that's why we got 1 left. F of k comes from k plus 1 minus 1 is just k. So that's how we got this equation here. But because of the induction assumption, we know that f of k is k squared. So we got k squared. Oops. Okay, I just pressed a key on the keyboard that I'm not supposed to. So so this becomes k squared plus 2k plus 1. And using quadratic equation stuff, you know that this is just k plus 1, the whole thing squared. And that's the end of this proof. That really is it. So you might want to identify, the steps, like, which part, why you can do it like this. The first part here is by definition of f. The second part is basically just looking at this. It's just algebra. The second step is purely algebra, which is this part here. The third step is making use of the induction assumption where f of k equals to k squared, because the theorem is assumed to be true when x equals to k. And then the last step is, also once again just algebra, because we recognize that k plus 1 squared is k squared plus 2k plus 1. So that finishes the entire proof. Let's scan this test and see if we have a case of proof by contradiction. Okay. Okay, so this one has a proof by contradiction that the algorithm returns non-zero if and only if there's at least one element in array A with the value of k. And so let's see how we can do this, using proof by contradiction. So once again, we have to separate what is given to us, which is the algorithm, and what we are trying to prove is certain properties of the algorithm. So I'm going to remove all these lines first. There we go. And then we'll go ahead and prove it. So in this case, we have to say, what is psi? Psi is given, is the algorithm. And then phi, which is the theorem that we're trying to prove, is identified by this algorithm returns non-zero if and only if there's at least one element in an array with the value of k. Okay, so we'll just copy and paste this here. Okay. So now you have to say what is the negation of the theorem. Not phi equals to, okay, there's at least one case where the algorithm returns 0 when there is at least one element in array A with the value of k, or, okay, so there's an or here, or this algorithm returns non-zero when, okay, I shouldn't use the word and, I should use when, and there is no element in array A with the value of k. So why is this not phi, a little bit different from the previous one? This has to do with if and only if. So when we use some random, I'm going to use a random letter here, okay? When we say A, if and only if B, this really is saying the same thing as A implies B, and B implies A. Okay, because that's just how we define equivalent to, or if and only if they mean exactly the same thing. And this in return becomes not A or B and not B or A. That is because of the definition of implication. So when you take the negation of this, okay, so we'll, on the next line, we'll take the negation. So when we say not, okay, and then I'm just going to be a little bit lazy here and just copy and paste this entire thing. Okay. In fact, I should be using the simplified symbols, but it's okay. I will just go ahead and do it like this for now. All right. So what we do is we apply De Morgan's law to distribute this not into the conjunction first. So that means we have to negate the individual parts. So not A or B. And then we change the conjunction into disjunction. Okay, and then we have not B or A, like that. But that in return, we have to apply De Morgan's law again, because what we do is we apply De Morgan's law to this part, and we also apply De Morgan's law to this part. So we are distributing the negation into the disjunction, but in the process, we have to change the disjunction into conjunction. So this part becomes not A and B and not B, or not B and not A. So now we just have to get rid of the double negation. So it becomes A and not B, or B and not A. And when you plug this into our theorem, which is saying this algorithm returns non-zero, which is A, if and only if the B part is there's at least one element in array A with the value of K. That is how we ended up with this particular not phi. So this not phi is saying, okay, we got two ways of making the theorem false, because we can have the theorem being false when the algorithm does return a zero, but there's at least one element in the array A with the value of K, or this algorithm returns non-zero, but there's actually no element in the array with the value of K. Okay. All right. So setting up up to this point is worth a bit of points already, because it shows that the person who's answering the question understands the nature of proof by contradiction. So now we just have to argue and say, okay, why is not phi why is the algorithm and not phi guaranteed to be false? So in this case, we have to refer back to the algorithm, and we have to say, let's do this part first. Okay, so we say part one, and we'll just randomly select that part one is this part. Okay, paste. So we have to show that the algorithm returning a zero and there's at least one element in array A with the value of K is not possible. Okay, why is that not possible? So what we do is we go back to this algorithm. Returning zero means I is less than n is false. Okay, so we start with that. Okay, we say returning zero means I is less than n is false, which also means I is greater than or equal to n after the loop. Okay. So if I is greater than or equal to n after the loop, that is the reason why we got out of the loop. Because when I is less than n, we do not get out of the loop. The other reason why we can get out of the loop is when A bracket I does equal to K. So those are the two reasons why we can get out of the loop. Okay. This means we exited the loop because I is greater than or equal to n. Now, can we get out of the loop because of I is greater than or equal to n, but also at the same time, there's an element of in the array A that equals to K. That is the argument. It is not possible. The reason why that is not possible is if we did have an element in the array that has the value of K, we would have exited because this condition is false. Okay, so we write it down here. Okay. If we exit the loop because I is greater than or equal to n, it means no element in A has a value of K, because otherwise we would, the algorithm, okay, otherwise the algorithm would have exited due to the right-hand side of the conjunction in the while condition, resulting in I being less than n. Okay, so that's basically what I am asking for, is to argue this way. So part 2 is going to deal with the other part of not side, which is this part here. So once again, we just copy and paste it here. And part 2 states that this algorithm returns a non-zero even though there are no elements in array A with the value of K. Okay, why is that not possible? Returning non-zero means, okay, typo. It means I is less than n when the loop exits. Okay, so when we go back and analyze the loop, when we exit because of I is less than n, that means this condition has to be false. Okay, this means the right-hand side of the conjunction, which is the while condition, is false. This also means A bracket I equals to K for some element in A. And this is contradicting because it contradicts there's no element in array A with the value of K, and now we say there is at least one element in A with the value of K. So that's how we finish these two parts. So once we know that part 1 and part 2 shows that not phi is false given the algorithm, and that concludes the proof by contradiction. So there we go. So that's the proof by contradiction in this particular test. And then we can, I think this is the this is the proof by contradiction of spring 16. So now we get rid of spring 16 and we'll take a look at fall 16. And in fall 16, the proof by induction 1 is this one. So basically, once again, it is about the same thing. You have to establish the base case first. And then once you have the base case, you perform the induction step, where the induction step makes an assumption that the theorem is true for a certain value of the parameter of the function. And then based on that assumption, you have to show that the theorem is true when you take a step forward. So if I were to generalize, okay, we can say, okay, I'm going to use equation here. Okay. So basically, we are parameterizing the theorem. So we can say, psi I is the theorem theorem parameterized with I. So in this particular case, in this question, psi I is basically saying, f of I equals to 2 to the power of I minus 1. Okay. Of the range of values such that, okay, of the set, okay, I should say, of the set S, okay, such that psi I is true. Okay, I should say it like this, such that for all I in this particular set S, psi of I is true. Okay, so this is basically just using symbols to kind of represent what we are talking about. So in this question, our so-called set here is basically Z star, which is the set of all non-negative integers, including 0. Okay. To prove by induction, select an element from S and prove, okay, select, let me say specific elements. Select an element, okay, I'll make this very specific, K in S, and prove that psi k is true. Okay, but we just need to prove that for this particular case, when we're only considering K as an element of S, that psi is true. Okay, to prove the base case involves selecting an element K such that this is true. So for this question, we select K being 0. Okay, so because by definition, f of 0 is 0, which is also the same thing as 2 to the power of 0. Okay, let me use the equation again. Okay, insert equation. Okay, f of 0 equals to 0 by definition, but that also equals to 2 to the power of 0, which is 1 minus 1, and as a result here, we have proven the theorem, but only when K equals to 0. So this is the base case. Okay. The induction step is generally like this. Okay. Assume that for some arbitrary, there we go. Okay, for some arbitrary K in S, psi, it would be nice if I can just, kind of, without using the mouse, I can start to enter equations, but Google Documents doesn't have that feature. So we say psi of K is true. But this is an assumption, okay? use this assumption to prove that. So once again, insert equation, psi k plus 1 is also true. Now, once again, whether it's k plus 1 or k minus 1 kind of depends on, what we are trying to prove, whether we need to go forward to larger numbers or we have to go backwards to more negative values. But the idea is the same. Okay, we make an assumption and then we say, okay, using this assumption, can we prove that the next step is also true? So for this particular question, the induction step assumes that for some, so we'll insert equation k in z star, meaning k is a non-negative integer. We know that psi of k is true. So psi k is true. Okay. All right, so now we oops, I just typed the wrong key again. Just need to find out where I'm supposed to be at. Okay, undo. There we go. Undo. Okay. Okay, for this question, the induction step assumes that for some k that is a non-negative integer, psi of k is true already. Need to prove that psi of k plus 1 is also true. Okay. So in this case, we can basically, this boils down to, okay, assume f of k equals to 2 to the power of k minus 1. This is the assumption. Okay. Then we can now say something about f of k plus 1. Okay, f of k plus 1 by definition is over here. It is 2 times f of k plus 1 minus 1, and then the whole thing plus 1. Okay. So then when we cancel out this plus 1 and the minus 1, as parameter to f, then we ended up with 2 of fk minus 1. But because of the induction assumption, we can now say, oh, but this is the same thing as 2 times 2 to the power of k, because that's the assumption, is 2, okay, I need to use parentheses here, 2 to the power of k minus 1, and then the whole thing minus 1. There we go. I'm just double checking to make sure that I didn't get it wrong. Oh, the plus 1. Okay, I take it back. I copied the equation incorrectly. There's a plus 1 here. Yeah, so I forgot about that. And okay, the definition is with a plus 1. So we got to do a plus 1 here. Okay, so that's where the confusion is. I'll point out, exactly where I got confused. Okay, so now that we got this one, we can now combine these two. 2 times 2 to the power of k combines to 2 to the power of k plus 1 as the power. And then 2 times -1 is -2, and then plus this one. So we have a net of -1. And that's the end of the proof, because that's what we want to prove is f of x, in this case x is k plus 1, is 2 to the power of x minus 1, and we proved it. So we say this shows that, okay, insert equation again. Oh, okay, insert equation. Okay, so this shows that f of k plus 1 equals to 2 to the power of k plus 1, and then the whole thing minus 1. All right, so we are done with this proof. Let me go back and restate, how we went from one step to the next. This part here is purely by definition. This is how we define function f recursively, which is stated up here. So this is given to us. There's no assumption here. And then going from this to this part here is only because we got k plus 1 minus 1, as the parameter to f, and that's why we can just cancel out the plus 1 with the minus 1, so we only got k left. So that's how we went from here to here. And then from here to here is just expanding f of k being 2 to the power of k minus 1, and that's because of the induction assumption. So that's why we turn this f of k right here to 2 to the power of k minus 1. And then from here to here is just algebra, because we distribute the 2 times, so that we end up with 2 to the power of k plus 1 here. And then we have minus 2 because of 2 times negative 1. But then we have a plus 1 here, which cancels out 1 of, which turns the negative 2 into negative 1. And that's how we ended up here. And that's the entire proof. And this is once again proved by induction. And let's see whether this one has proof by contradiction. It does. Okay, so it does have one that is proof by contradiction. And I'm going to continue with this video a little bit later. So I'm going to stop the streaming at this point, and we'll have a second stream just in a little bit.